Start off our program with the keynote speaker, but we're taking a short interlude, if you will, to make a presentation for the TDWI Best Practices Awards. Quickly, the little background, as you know, TDWI is the premier source for learning, education and research, data warehousing, business intelligence, and advanced analytics. And so, thus our role is to look at and to share with the industry best practices in a variety of areas within the data warehouse technology stack. Every year we put out a call for papers, and we have our faculty judge the different projects that are submitted. And it's our pleasure to make the awards for those particular programs here today. To offer a little bit of background in the award winners and to introduce them and to present some awards, I'd like to introduce my colleague Philip Russum. Philip is the Director of Research for TDWI, has been a research analyst for over 20 years, brings a wealth of experience to the area, and also was in charge of judging the programs that were submitted. So, Philip?
Thank you, Rich, for that introduction, and I'd like to repeat his thanks to all of you for attending TDWI Boston. Let me find my equipment here. It's the big green button, right? There we go. You know, we've been offering awards, I think, around 16, 17 years now, and every year we revise the categories that we give awards in, and it's because some of the older topics sort of fall from favor or aren't as interesting, or just simply become broadly done by a wide range of organizations. So this year we ended up with 11 categories, and you know, we don't always give an award in a category. If none of the entries seem to deserve an award, we just skip it. So out of the 11, we have 10 awards. If you would, hold your applause to the end, because we just need to move this quickly, and you might want to hold on to your hats. I'm going to go through this pretty fast. So I'm going to do this in alphabetical order. The first award category I want to look at is Advanced Analytics, and our winner this year is Scotiabank. And we have Neil Freyka and Vic Machito from Scotiabank here. The reasons the judges gave them an award is that Scotiabank created a new pricing model for unsecured loans, and the BI and data warehouse team supported this new process by developing multiple analytic models, a new data mart, tight integration between the warehouse and operational apps to make this new pricing model really, really work. And it paid off for the company, because the impact is that data warehousing and analytics are able to deliver price recommendations into operational applications, so very tight integration between those. And this assists 4,000 users, so this is very significant. So again, Neil Freyka and Vic Machito from Scotiabank. Next category is Business Intelligence and Data Warehousing on a Limited Budget. You know, we've actually been giving an award in this since the very beginning. This is one of those categories that never goes away, because budgeting and the cost of BI and data warehousing is always very important. So this year's winner is Hdfc, Standard Life Insurance Company Limited, based in India. And a fellow with a very long name is here to pick up that award. I'm going to call him Anand. So Anand is the VP of Business Insights. Reasons for the award: HDFC enabled a strong performance management platform, not just a reporting tool, but also action-based dashboards. And this improved operational efficiencies, which improved, in turn, customer experience. And they even have early warnings for the sales department, right? So a lot of impact for the business despite a very modest budget. So congratulations to Anand and his colleagues. Next category is brand new for us. It's on big data technologies. You know, big data is in the press, and we have a lot of TDWI members and other people that we serve in our community who are addressing big data in a variety of ways, typically with some form of analytics. So the first winner in this brand new category is Ad Marketplace, represented by their CTO, Marco Uden, and their solution sponsor, Chris Salen from HB Vertica. So reasons for the award. Due to their business as a kind of online advertiser, Ad Marketplace deals with a lot of click data for these advertising click-throughs. And this kind of data for them has to be processed in real time to predict the relevance of these clicks and also assist their customers who are using that data for their sales efforts. They're using some of the buzzier technologies like Hadoop, columnar databases, NoSQL, predictive analytics, and this has had a huge impact not only for the volume of data but processing it real time, a huge impact on their business, which after all is a business based purely on data. So congratulations to Ad Marketplace. Next category is emerging technologies and methods. We've been doing this category for 3 or 4 years now. The winner is, I forgot to tell you, emerging technologies, kind of a big bucket of kind of the newer stuff. Things like text analytics tools and methods go with that. Some of that stuff I mentioned with big data, so Hadoop, NoSQL. But also methodologies like agile and lean development methodologies. So our winner this year is Aircell Limited, based in India. And we do not have a representative here, but so briefly, they were able to build a unified marketing platform project. In other words, analytics for their prepaid mobile market that they serve. So analytics there just help them drill deeper into more penetration for that marketplace. Next award category, Enterprise BI. This year, Enterprise BI can be a lot of stuff. Quite often it ranges from enterprise scale, operational reporting, to basically anything that has an enterprise scope to it. You know, so these tend to be very big, broad topics with thousands of users. And this year, the winner is USAA, a well-known insurance company based here in the U.S. So they built a data mart that consolidates data from member calls, other channels. And the impact on the business is that the reports based on that data allowed them to optimize call routing, sales, and service, plus improve the experience of most customers. So that's a lot of impact, coupled with innovation through agile methods. So we have Sarah Andreas and Stephen Bruley here representing USAA. Congratulations, guys. Next category is enterprise data management strategies. Again, this is a really broad bucket of different stuff. It can range from data quality and data integration stuff all the way up to managing big data is kind of one of the hot issues here recently. It could be metadata management, master data management. So this year's winner is the company who wins the award for the longest acronym. So TIAACREF, I think it's pronounced TIACREF. And we have Joe Sikowski, their CTO, and Bob Bernard, Senior IT Manager. Reasons for the award, a lot of innovation. They founded a data transformation program using service-oriented architecture, dashboards, visualization, and a graph database. And this had a lot of positive impact for TIACREF in that they were able to improve business outcomes and operations. So congratulations to these guys. Next category is enterprise data warehousing, something that's probably close to all of our hearts here, right? Most of you are data warehouse professionals. And the winner here is Caisse de dépôt et placement du Québec. And we're represented by Sébastien Dupré, Director of the Business Intelligence Competency Center, and also Robert Lepin, who's the Senior Vice President. So it's a very innovative architectural approach based on this very new method, at least new in North America, very common in Europe, called the data vault method. It's similar to what some Americans are doing with the so-called data lake. Also innovative use of services, innovative methodology for ETL, and so forth. So it was really innovation, innovation, and innovation that got them awards. So congratulations, guys, at Caisse de dépôt et placement du Québec. Next category is government and nonprofit. The Denver Public Schools are this year's winner, represented by Stan Razor, and their solution sponsor from RevGen Partners, Kirk Mellons. So again, innovation was an important part of getting the award here. Denver Public Schools built a customized performance management system. You know, taking methodologies we typically apply to corporate performance management and quantifying the performance of school systems and whole school districts and all the way down to teachers and students. Obviously, that would have a very big impact on a school district, and that's why they got the award. So congratulations to Denver Public Schools. Next category is performance management, and many of you do that. You've been doing it for years. It's a methodology based on measuring aspects of the business through metrics and key performance indicators. This year's winner is Dell, and when I say Dell, this is actually internal IT at Dell. This is not one of their product divisions. And so Dell IT built a global BI performance management solution, and it's big because it embraces a $40 billion supply chain plus financial executives. And they measure both they measure both daily operations and strategic initiatives. And they were able to quantify a savings of $3.2 million through this action. So getting the award today would be Jeff Mars and Wishar Dattari. So congratulations to Dell. Next category is Right Time BI, and this year's winner is ComData, and represented by Tom Pierce, Todd Joseph, and Andrew Stewart from the Solution Sponsor Company. So a lot of impact that the judges saw in this award entry. They built a product internally called Fleet Advance, and it's an analytic solution for commercial transportation fleets. It enables them to do smart fueling. It's very innovative because it has real-time dashboards and scorecards, plus analysis of historical performance. The relevance is that we just thought it was the kind of thing that a wide range of companies could do, right? So it's relevant to companies in all kinds of industries. All right, so congratulations to ComData in the Right Time BI category. All right, folks, almost done here. So those are the awards. Congrats to all the winners. Let me tell you that there will be some peer networking with the Best Practices Award winners, or at least with some of them. And this is an opportunity to meet some of the award winners and talk to them about what they're doing and try to learn from them. That's the point, right? So when and where? It'll be tomorrow, 11:15 to 12:45 during the lunch that'll take place in the TDWI exhibit hall. Most of you are going to be there anyway, because that's where you get your lunch as part of your training and other stuff here. So look for a table with a sign BP winners, and with any luck, we'll find some award winners there to chat with. And I want to encourage all of you in the audience to think about submitting an award. You know, anybody can fill out the forms and submit an award, and it's a way for you to get recognition for what you and your peers have done where you work. If you go to that link up there, tdwi.org/BP awards, you can get all the details. Or you can just go to our website and search for awards, and you'll find it. So the timeline is in January, we'll make our annual announcements, and then sometime in April, the awards will be due, and then we'll announce winners in June. So if you have a implementation of some sort or some sort of program, think about writing that up for an award. So here in conclusion, I want to say thanks to a lot of people. First of all, thanks to the judges. You know, we have about 20 different individuals who volunteer their time and expertise. Don't forget, our biggest business really is training, right? So most of the judges are people who are in the field doing hands-on work with BI, data warehousing analytics every day, and it's great to have them judging these awards. Congratulations to all the award winners. I know it's great for them to get recognition. And finally, you can read about these awards. Here's another URL for you to jot down, or you can just go to our website and search for awards, and you'll see descriptions of these award-winning categories today. So in closing, let's have a really big round of applause for this year's winners.
Congratulations to all the winners, and we hope you'll take advantage of their presence here today and next few days as far as your networking is concerned and successful projects. It's my pleasure to introduce the speaker for our keynote, Tim Buckman. Dr. Tim Buckman is the founding director of Emory's Critical Care Center, which is integrating intensive care units throughout the Emory healthcare system. Dr. Buckman is past president of the Shock Society, the Society for Complex Acute Illness, and the Society for Critical Care Medicine, the latter being the largest organization of critical care professionals worldwide. Before joining Emory, Dr. Buckman served as the Edison Professor of Surgery and Director of Acute and Critical Care Surgery at Washington University in St. Louis. Prior to his 15 years on the faculty at Washington University, Dr. Buckman directed the Surgical Intensive Care Unit and founded the Trauma Center at Johns Hopkins University in Baltimore, where he completed his surgical training. It's my pleasure to introduce Dr. Tim Buckman.
Well, good morning, everyone. It's a tremendous pleasure to be here with you in Boston this morning. I'm going to speak on better health, better care, and lower cost, and how big data and real-time analytics can help us achieve this triple aim. I want to talk a little bit about innovation because sometimes we forget what the word means and where it came from. It really came into usage around Shakespeare's time. It comes from the compound Latin in and novus, meaning into and new. And in Shakespeare's time, it meant something along the lines of making changes in something that was already established, more like development or evolution. Our modern meeting, and the meeting we're going to talk about today, is really about the introduction of something new. This is transformational and revolutionary for healthcare. Many of you have had relatives or have been a patient in ICU, but I suspect some of you have not. I want to talk to you a little bit about critical care, and that's going to be the topic of our conversation today. Critical care occurs when there's the existence, or at least the likelihood of a life-threatening condition that either requires constant monitoring, attention, or in fact intervention. The synonym for critical care is intensive care. And intensive, again, comes from the Latin, intensus meaning to tighten, and cura meaning to care. So when we talk about critical care in ICUs, it means that we're tightening care when there's an immediate threat to life. So innovation in critical care, and that's what we're going to be talking about this morning, occurs when there's a change in what we do or how we do it when confronted by a patient. It could be you, your spouse, your child, your parent, your relative, your coworker, patient who has or is likely to have a threat to life. So why do we need to change? I mean, is there a reason that we have to do things differently? Well, this is the talk map. I'm going to talk to you about the origins of critical care, talk about how necessity drove innovation in the early years. I'm going to talk a little bit about false hopes and the need for data and analytics in critical care. I'm going to spend a lot of time on the concept of situation awareness, because that's where you and your companies and your resources are actually going to make a difference in how we care for patients. And finally, I'm going to show you a little bit about how real-time analytics are actually creating and delivering new value in critical care. And we'll come back to that value proposition several times. You want a reason to talk about value. It's a picture in a typical ICU. This one happens to be from one of my colleagues in Case Western. There are about 18 devices in the room, and I will tell you about 30% of inpatient costs, close to a third of all hospital costs, are spent on the fewer than 15% of the beds that make up critical care. So there's real money here. Now, let's have a look back. Let's talk about how necessity drove innovation. And in fact, the history of critical care is one of meeting new clinical needs. That's different from treating heart disease or respiratory failure or some rash. We are finding patient need is directly driving the evolution, the revolution in critical care. We can go back a little under 100 years now to Walter Dandy. The picture there of the dome is Johns Hopkins Hospital. Dandy invented many neurosurgical procedures, such as clipping brain aneurysms shown in the figure. But he noticed something. He noticed that as a surgeon, he wasn't perfect. Patients got into trouble after operating. And maybe it would be a really good idea to park the patient in a place where people who were experienced at looking for problems could find them and recognize them sooner. He was the person who invented the first post-anesthesia care unit, the first recovery room. Effectively, he was the guy who invented the idea of an ICU. Now, amazingly, not much happened for about 20 years after that. Since we're in Boston, I thought I would remind you of this event that occurred in 1942, not so long ago. It was wartime. It was the Boston Holy Cross game. It didn't come out all that well, the football game, but what came out even worse was a nightclub fire at the Coconut Grove nightclub here in Boston. And what happened was that, as happens today, the people who were running the nightclub decided to lock the back doors so that nobody could get in the back way. A waiter was there trying to change a light bulb. Unfortunately, there was no light where the light bulb was. He didn't have a flashlight, so he had to lit a cigarette lighter. They had cigarette lighters in those days. Caught the drapes on fire. The place burned to the ground. 400 people were killed. But that's not the key part of critical care history. The key part of critical care history is that there were 39 survivors. And 39 people were taken to the Massachusetts General Hospital within the space of 3 hours that night. Now remember, there was no such thing as an ICU at that time, but they had 39 people with more or less identical injuries all show up at their doorstep within about 3 hours. It became quickly apparent that the only way to care for these people was to care for them by teams and use protocols. The team-based care involved rapid prototyping, sorting through who the patients were, skill acquisition, development, skill diffusion, and then protocols. We're going to do the same things the same way every time. In fact, this innovation caught on very quickly, spread to the wartime theaters throughout Europe, and the idea of cohorting patients with people and plans on how to take care of those patients, that seemed like a pretty good idea pretty fast. But the idea of an ICU with continuous nursing care spread even more rapidly in this country. And by the late 50s, early 60s, you started to see pictures like this, quote, an actual ICU such as it is back in the late 50s. You'll notice circled there in the upper left is an IV bottle. Down there on the lower right is an addressograph. We still have those things hanging around today, although the addressograph is more commonly a label printer. But I call your attention to the patient in the bed who's up there smiling and so forth. That patient today wouldn't be in an ICU, wouldn't be in a hospital. That patient would be at home. It looks a little different today. It was a massive national effort building these things right around 50 years ago. This is from St. Luke's. And what you'll notice is that there are an awful lot of people. They're wearing nurses' caps and not much equipment. The contraption you see there, a circo-electric bed, was simply designed to turn the patient over and over after a spinal cord injury. The key thing is there wasn't much data and there wasn't much technology. So the first third of our history in this discipline was simply getting people and experience together. We didn't have machines generating data, and we didn't have anything to fix them with. We didn't have anything to do with the data. That changed. Just out of curiosity, when you go into a hotel today, I assume you look where the fire escape is. Do you look where the AED is, where the defibrillator is? No, you don't. You might think about which one's more likely to save somebody's life next time you go into a public place. Look around, see where the AEDs are. The defibrillator, as you know it today, as you've seen it on TV every week for the past 40 or 50 years, is actually a 50-year-old invention. This paper came from the New England Journal of Medicine in 1962. Okay. It's just that new. So this was the beginning of machines, ventilators, dialysis machines, defibrillators, things that snake in and out of the body. We spent a lot of time over the past, say, 50 years inventing the machines. Interestingly, it was also about 50 years ago that computers started to make their way into the ICU. Hal Weil and Herb Shubin in 1966 described the efficient monitoring with a digital computer, cardiovascular function in seriously ill patients. And if you look down there at the bottom in the middle, you'll see the prototype of the original monitor that was built. This was drawn in 1977. That bedside monitor that you see in every TV episode of a medical show, that's actually, that display is a frozen accident. We'll talk about why that is a problem and some solutions around that in a moment. But indeed, they were hooking the patient up to computers. They had CPUs and, card reads and punches and so forth. They had data streams coming out. So we had a race on, the rise of the machines and the rise of the processors to crunch the data coming out of the machines. They understood the importance of trending. This is an automatic plot from about 50 years ago now. What I've told you so far is that our most successful innovations have been supported getting people and processes together. They've been simple, and our need for our most successful innovations have been created in direct response to a newly identified clinical need. If you synthesize that, you'll get to one of my key points. Initially, technology is the enabler of change, not the driver of change. Let's talk about the rise of the machines and what it looks like present day. A sketch of some of the things. This is a mock-up of what it actually looks like with a mannequin inside the room. There are a lot of devices in there that are generating data. And we have a data overload problem. In fact, if you go into a typical ICU and you are a clinician like me looking at a single patient, you will be confronted by 200 or more interrelated variables. They're all talking to one another. Unfortunately, as you know from the psychology studies, we can keep track of between 3 and 7 things at once. You get over 7, even the smartest among us loses the relationships. And the truth of the matter is, most of us think univariate in a multivariate world. That's where you guys are going to come in. Which leads me to the second chunk of this talk, which is a talk about situation awareness. I want to talk about Micah Ensley's concept. Micah Ensley is now Chief Scientist for the United States Air Force. She described this about 20 years ago now. And she talked about 3 levels of situational awareness. We're going to talk about this a fair bit, involving perception of data, comprehension of how the data fit together, and the ability to project what those data are telling you into the future. That is different than making more data. And if anyone here thinks they're going to make inroads in healthcare by producing yet another box that produces more data, go back to square one. Won't work. The information we need is not going to come from producing more data. We're going to do that all on our own. We're going to give you more sensors and more stuff to work with. It is the insight that allows us to find, sort, and integrate and process those data that actually leads to actionable information and doing something new, better, faster for patients. I like to make this analogy because it's actually true. This is obviously a drawing, but it might as well have been me growing up in the 1950s. On Sundays, my dad, OBGYN, still in practice, goes to the office 4 days a week to escape my evil stepmother. That was a joke. Okay. We would take a Sunday drive. Now, my dad is a brilliant clinician, a terrific diagnostician. His navigational sense is lacking. So we'd get about 10 miles north of New York City. He'd stop into a service station, get this thing called a map. Some of you may have seen one. Okay? Get some instructions about where we're supposed to go. I'll go about a mile down the road, turn right, you'll intersect this road, so forth and so on. He'd get thoroughly lost, stop into another filling station. I was in the back seat. The pile of maps would grow larger than me. That's the way we did it. A map was a space of infinite possibilities. It was really easy to get lost. We'd take a back road, take a blind path. We'd lurch forward. Most of the time, we'd get where we wanted to go. Sometimes we didn't. We'd turn around and just head back. Then when Netscape came out and MapQuest came on board, we all got really excited. Because here it was, you could enter an origin, you could enter a destination, you get a 10-page printout of turn right, go 0.37 miles, turn left, go 0.15 miles, and so forth. It worked really great until one of 2 things happened. You would either hit road closed, there was an accident or a flood or something like that, or more commonly, you'd be talking to the person next to you, you'd miss the turn, and all of a sudden you'd be at some place that didn't appear on the list of directions. You were completely and thoroughly lost. As long as you did things perfectly and the environment helped, sure, it worked. But sometimes it didn't. Now, I don't think any of us navigate this way anymore. We use something that looks like that. Might be a standalone device, might be an app on your smartphone, doesn't make any difference, but we use this. Now, that are the data that are going into the device. It's not the data that makes for situational awareness. It's the analytics behind the data and the visual display. That's what comes out of the data strings. That's actually what we need for healthcare. It feels right because, once again, you can perceive the data, gee, I'm located at this intersection. You can comprehend what it means. Oh, this intersection is part of a larger grid. And you know if you follow the magenta line, you're going to get there about 10:01 a.m. You have a little bit of information about the environment. The traffic's favorable. Your speed's only 20. You can go about 10 miles an hour faster. Stop the guy honking behind you. This is situation awareness. So if you are going to do something to help me take care of patients, you have to help in one of those domains. You have to help with perception of the data. You have to help accumulate it into a common processable form. You have to help me understand how those 200 variables are interacting so I can recognize patterns, processes, and trends. And you have to help me project into the future to understand if I do nothing for the patient in the bed, this is what's going to happen. If I choose treatment A, I'm going to get to state A prime, B, B prime, and so forth. I need to have perception, comprehension, and projection to do my job. Remember this from about 15 years ago? This did not work out really well because people spent all their time looking at the devices and we ended up with things like this. Adding another screen and another box will not help. Let's talk a little bit about ICUs in the present day. Loss of situation awareness is easy and common because the displays have got multiples of these strings of waveforms and numbers. They represent about 6 seconds worth of data, and if you have 20 of these and you look away for a minute, you cannot remember what happened a minute ago. And that creates a problem when you've got teams of people going from bed to bed, because it's not just how I understand the situation, it's how every member of my team understands the situation. And when we talk about team situation awareness, we have 3 failure points. Once again, in perception, have we really communicated the information across? Do we really understand what we're looking at here? Second, am I interpreting the data the same way you are and you are and you are and you are? And furthermore, are we actually projecting things forward in time the same way? Because as soon as I, as the boss, walk away from the bed, everybody else in that picture is going to go about their business doing what they think is right. Doesn't matter how much I say this is what you need to be done. If we don't have the same mental model and understanding of where we think the patient is going, we are not going to effectively care for that patient. So we talk about situational awareness. There's direct observation, there's system input, but there's communication from the team. We actually all have to be on the same page to do our job effectively. And we have data flowing at us at a rate that approximates, I'm going to just tell you, it's about 10 to the 3, 2 times 10 to the 3, 5 times 10 to the 3 bits per second. That's a problem. So we actually have to organize information around common goals. We have to support global situation awareness. We have to make critical cues salient. And importantly, when we are doing team activity, and healthcare is all about team activities, we actually have to build a common picture to support team care. Let me go back to this picture I showed you. There are 18 devices plus the paper in the foreground in this picture. I'm not going to count them up for you. But I'm going to tell you that if you are a nurse and you've got 2 of these patients, you cannot possibly absorb those data from primary sources. It doesn't work. Moreover, we're human. We get distracted. So if the task is just checking to make sure that the alarms are set properly and the ventilation on the machine is set up properly, and I come in and say, can we do a shift change handover now? That's an important process. But if I interrupt you while you're doing those things, those simple alarm and vent checks, you will forget to go back to them 1 out of every 4 times. So not only are the data coming at us, we have to deal with our colleagues, biological needs, the telephone ringing, so forth and so on. Huge opportunity for error, but huge opportunity for technology to come to our rescue. I don't have to present the 4 V's of data to this audience. You know about the volume, the velocity, the variety, and the veracity. Our needs in medicine are no different than they are in the defense industry. Okay? We have to deal with all 4 of these. But we're asking in the moment, what's the current physiologic status of my patient? What is the trajectory of my patient? And there are 3 P's that matter to healthcare over and above those 4 V's. It's worth paying attention to these, because if you're going to be successful in the healthcare marketplace, you've got to recognize how we think and function. The first thing is that biology and pathological states don't occur in a continuum. It's lumpy. The patients on this side of the room who have congestive heart failure look much more alike than they do look like the patients on this side of the room with respiratory failure and the corner with renal failure. They look alike, they clump, they cluster. In order for us to be effective in caring for those patients, we have to get very quickly to the probabilities of what state that patient is in. Second thing is, if I tell you and I tell you I'm going to treat you the same way, you're not happy with me. You want personalized care. You should probably have personalized care. But when I personalize care, I have to do it on 3 time scales. I have to deal with what you're born with. I have to deal with what you've acquired during your many years on this earth. And finally, I have to deal with what got you to my ICU in the first place. And if what got you to the ICU involves a drug that is metabolized differently in 15% of the population, and you happen to be one of the lucky 1 out of 6, not only do I have a problem, you have a problem if I prescribe the standard drug. So I actually have to integrate data across those timescales. And then finally, I have to make predictions. I have to make predictions about what's going to happen 5 minutes from right now, 5 months from right now, and 5 years from right now. Because it's not just good enough for me to get you out alive from the ICU. If I get you out alive and you go home and you can't go back to work and you can't feed, bathe, and dress yourself, neither of us has succeeded. I'll just standardize and give me a checklist. Okay? The aviation solution. Disclosure, I'm an airline transport pilot and flight instructor. Standardization and checklists are not all that we need. This is what we're actually trying to do. Any of you who've been on a naval warship will recognize this. We are trying to detect a problem, track it, classify it, and project what a threat might be doing. We have to make a decision about what we're going to do, assign tasks, act, and then evaluate the outcome of our actions. This is what it looks like today. This is where I'm going to be tonight at our electronic ICU center. We have people trying to process torrents of data, often coming in very different forms, whether they be traditional displays shown in the upper left, graphical glyphs, high-definition audio-visual, all sorts of stuff. We've got human brains trying to process this stuff. And the gentleman up there in the upper left in the screen, at the time I took this photograph, he was looking at 72 patients simultaneously. We started to scratch the surface with the technology. We are not there yet. What is it that clinicians actually are interested in? They get data, they try to define a present state, they try to understand what the trends are, and they use the trends to forecast what the patient is going to be doing at some point in the future. This is how clinicians tend to think today. They think this is what they want. There are reasons for this. We can get a present state in a single dimension, such as blood pressure, shown here. We can get it in multiple dimensions. This is sort of a classical monitor display. Does this make a difference? Yeah, it actually does make a difference. It's one of the pieces of evidence that shows you it makes a difference. If you can detect the fall in blood pressure early enough, you can save lives. This graph simply shows that if you happen to come in with an infection and your blood pressure is going to fall because you are becoming septic, how soon I recognize that and treat you makes a difference. In fact, every hour that I delay treatment, according to this graph, and this has not been overturned, this is accurate, every hour that I miss treating you with antibiotics that are appropriate to your infection, your mortality goes up 6%. I have a 6-hour delay because I'm tired, sleepy, or otherwise occupied. Your mortality from your infection has increased by 1/3. So, yeah, it actually does matter, even that simple single-dimensional stuff. About 30 years ago, people said, gee, maybe we ought to display all these data indexed and normalized and referenced. That was what the conception was on the left. Of course, the conception was preceded about 25 years earlier. You may recognize the picture on the right. That was Dr. McCoy's sick bay on the original series of Star Trek. Same idea. But we got to the idea that you needed to trend this over time. And trending over time does make a difference, because if I show you a display that looks like this, you say, gee, the blood pressure is a little low, the heart rate's a little fast, but if I add the trending information simply to the bottom of the display, very simple data processing process, much easier to recognize that this patient is in septic shock. Does this trend detection matter? Yeah, it actually does. So this is where I wash some of our dirty laundry in public. I took this picture 4 years ago after the dust had settled. This was a display that I could only reach after 8 mouse clicks. What it shows, the orange line is the heart rate. That held up pretty well. The green line is the oxygen saturation. That didn't hold up so well. Over about 40 minutes, the patient was desaturating until right around 8:10 in the morning, the end of the arrow there on the right, the patient had a cardiac arrest because nobody noticed. Too much data. This patient did not do well. It doesn't happen anymore. I took this the other night when I was sitting in the EICU. Colors are a little different, but you see that red thing there at the top? That's the oxygen saturation. We detected it early, got the right people in the room, fixed the problem. Patient is alive today. There were no consequences because there was no really bad event. We've learned to find these things and fix them. If you want to know where all this is going, it's not detection, it's prediction. With big data, good models, and high-performance computing, we're not going to just be able to do predictive physiology and predictive pathophysiology. We're not just going to be able to predict the weather, we're actually going to have something to do about it. We're going to be able to predict what a pathogen is going to do, and in fact predict how pharmacologic agents are going to interact with the host and the pathogen to kill the pathogen but not hurt the host. And we do want it to be pattern personalized and predictive. We do want to be able to look ahead as part of situation awareness so we can make the right choice for the right patient at the right time. Now, this is not a new concept. This again goes back about 25 years. This is the same picture as I just told you with the cardiac failures over here, the respiratory failures over here, the kidney failures over there. But detecting it and having that idea goes back to a man named John Siegel who died a couple of years ago. About 20 years ago, he said, you know, what we can do is classify deviations from normative states. And he said we can get prototype deviations and define those as the center of mass of certain types of diseases. And he said we could put these in a high-dimensional space. Here it was shown as a three-dimensional space. And although it may not be clear to you from just glancing at this, you will find the circles who are the survivors partition away from the pyramids who are the dead people. So understanding where you were in the space would predict your outcome. We now have automated classification systems. This is from my colleague Mitch Cohen, published a couple of years ago, that can take multidimensional data and even through unsupervised machine learning can identify what block of space the patient is occupying. So this is where we're actually going. On the top, I show you what clinicians think they want. On the bottom is what clinicians actually need to have in order to do their job. They need to know what the likelihood is of transitioning from one part of that state space to another. If you're in a bad part, we want to know what drug is going to facilitate transitioning to the good place. If you're in a good place, we want to know how to keep you there safely. Let's talk a little bit about how we need to do that together at the bedside. Some moving data. You're all used to looking at EKGs and the standard monitors. It's quiz time. This is your heart rate, or 4 people's heart rates, displayed as you're not used to looking at them. Not just a little number on the side, but trending over time. I will tell you that the average heart rate for each of these displays is about 65 to 70 beats per minute. You're looking at 30 minutes worth of time. And I will tell you that 3 of these people are sick and 1 of them is well. All I want you to do is look at those patterns and ask, who's the healthy person in that group? Well, for those of you who picked A, I'm really sorry, that's heart failure. If your heart rate doesn't vary, you have a problem. Take your own pulse, breathe in, breathe out. You'll feel your pulse speed up and slow down. No, C is not the correct answer. That's a sinusoidal oscillation over the space period of about a minute. You can phone a friend. D is uncorrelated randomness. This is atrial fibrillation, one of the most common abnormal rhythms that afflict older folks in the United States. It causes strokes. We anticoagulate people and get them into trouble from the blood thinning process. You actually want to be here, okay? Scale-independent fractal variability. It turns out that multiscale fractal variability is a signature of health, and there are really only 2 ways the pattern breaks down in the single-scale periodicity, which can be flat, of course, or uncorrelated randomness. So here's an opportunity for big data to give us very rapid insight into how healthy or sick you are, just by processing the beat-to-beat variability, the reciprocal of the heart rate. Now that I've told you that, you can figure out which of these 2 patients did well, patient A or patient D. Both of them were septic. Similarly septic, the first 24 hours of data are shown here. The patient in the column on the left with the variability did just fine. Thank you very much. The patient on the right was dead within about 24 hours. We want to have healthy variability. When that variability goes away, it's a sign that things are not going well. Does this actually matter? Does this actually matter to healthcare? A couple of years ago, my colleague Randall Moorman at the University of Virginia published this article. His target population was babies in a neonatal ICU, very low birth weight infants, very fragile little people. He went to 8 hospitals, 9 ICUs, found 3,000 babies, and added an analytic onto the conventional EKG. He had an analytic under the conventional EKG, which looked at heart rate variability, especially deceleration. And he put up a number. The number here is 1.52. That's the fold increase in death predicted for the baby. The range for this was 0.5, meaning the baby had a lower than average prediction, all the way up to 4. Meant the baby was at least 4-fold more likely to die. He didn't give a diagnosis. All he gave was a number and said, look at this baby. Just look. See what's going on. Use your clinical brain. Now, I said there were 3,000 babies that he put this analytic on. He blacked the screen on half the babies, okay? Half of them, the screen was turned on. Half of them, the clinicians had no more data than they usually had. It was a 22% reduction in mortality. 22%. I put it to you, if this data-driven prediction was a drug, that 22% reduction would be a blockbuster. People would be lined up around the block to pay for the rights to license this and put it in the pharmacy. So what we have to do is we have to re-engineer critical care. Our current care just looks at patients and conditions, and we do the best we can with standardization. We actually want to specify populations and care paths so we get algorithms, situation awareness, and we activate caregivers and patients. That's what we're doing in the ICU. What I'm going to talk to you about in the last few minutes is some of the things that we're doing to recognize physiologic decompensation as it occurs, to classify by actionable mechanism, and then to mitigate by reversal of the cause and supporting treatment. That means we have to harvest data in motion, big data in motion, do real-time analytics, and generate an intuitive display. This is how we're doing it. Our shop, we happen to use GE monitors. We harvest the numerics and the waveforms. The waveforms are coming across at 240 hertz. We're typically harvesting about 6 of these different types of physiology. We plop them into a system called Bedmaster, and then we use a system called IBM's InfoSphere Streams. How many here are familiar with streaming computing? Show of hands, a couple of you. Let me talk to you about the difference between typical data mining and stream computing. In typical data mining, you have a big database, but that database, at the moment you query it, becomes static. You can write an infinite number of queries, you can do as many as you want, but while you're running the queries, you can't really update the database. In stream computing, you invert the model. You have rivers of data, torrents of data. You have sensors stuck into the data streams. The sensors are detecting anomalies in the patterns. It is a low latency paradigm. When there is an anomaly detected, it is pushed out as a change in yet another stream. And it provides literally instantaneous identification of things that are going on in the river. This is what it looks like in our environment. We have a variety of sensors. We drop it into the Bedmaster Data Hub. We have 3 layers to our stream computing. There's an adaptive layer, an analytic layer, and a delivery or a display layer. And we show the results. This is what it looks like. I'm not going to show it to you in real time. We don't really have time for that today. When you look, there are a variety of different patterns in this display. Each pattern represents a patient in a bed. And you'll see that the 2 in boxes kind of look like one another. And if you look really carefully down in the lower right, you'll find a third that looks similar to that. That's a patient, those 3 are patients whose oxygen levels have dropped and nobody has noticed because the alarms at the bedside are going off at such a rate that the nurses can't figure out what's going on. But by looking at patterns which our brains are designed to recognize, we can say to the few nurses that are there, go to those 2 and then that 3rd room that I just mentioned. We can test new analytics really easily because, quite simply, if we can code it in MATLAB, we can drop it in and see how it performs. So we will take a new algorithm, we'll write the MATLAB script, make sure it works, put it in the wrapper, put it into the stream, and we will get something new. This is called a synchrogram. You've never seen one because they really haven't been described before. But remember how I told you that your heart rate and blood pressure, your heart rate and your respiration talk to one another? You breathe in, your heart slows down. You breathe out, your heart speeds up. Your eyeball will tell you that the left 2/3 of that picture are different from the right third. Each dot is a heartbeat going along the x-axis. Along the y-axis are 4 pi, 2 respiratory cycles. The left 2/3, you can see that there's some synchronization between the heart and the respiratory cycle. On the right third, it has fallen apart. That's what people look like when they're going into respiratory failure before a doctor, a nurse, a patient, or a family member notices. But your eyeball is good enough to pick out the change in the pattern. So we're integrating that stuff now. We are integrating both coarse grain data shown in the glyphs above the graphical census that allows us to look at changes that are happening over time scales of hours to days with the fine grain data stuff that's going on a minutes to seconds time scale. And where we're really going with this is creating safety. It doesn't matter whether the patient is, whether they're in air transport, the operating room, or an ICU. Doesn't matter whose EMR it is. Doesn't matter whose display it is. Doesn't matter who's archiving it. As long as we can get the data and do real-time analytics, we can get early warnings and keep patients safer. This is a lot like air traffic control, okay? The job of the air traffic controller is not to fly the individual airplane, it's to keep the airplanes from running into one another and, more importantly, from running into the ground. That is what we are doing. We are now looking at 125 patients simultaneously. 1 doctor, 2 nurses, 125 patients. And the reason we're doing this is because we are trying to get to that triple aim. Better health, we want the patients to do better. Better care, we want to be more efficient and effective with our care processes. And let me emphasize, lower cost. The technology has to outperform the people. It has to enable the people to do their jobs. If you have not seen this month's issue of Health Affairs, go out and buy it. It's all about big data in healthcare. I want to make the point that advanced analytics are great, big data computing is great, but you want to be able to do it in real time. You want to get to that pink square. You want to be able to harvest big data and process it in real time so that people can make decisions that lead to the right care right now, every time. Let me close with 2 cautions. The first is the federal government has got its own ideas around big data. This was published in May. It's available on the internet. I would suggest you take a look. The executive branch is concerned about a couple or 3 things, or actually a couple or 5 things. First, they are really worried about privacy. They are worried about how we are educating people to use big data. They are worried that big data is going to be used in a discriminatory fashion. They are deeply worried about misuse of big data, particularly in law enforcement. And finally, they're asking all of us to figure out how to get the data safely, which means appropriately anonymized, into the public domain. I got a letter about 3 weeks ago sent to me by a national thought leader, somebody who was very involved in defining this triple aim of health, care, and cost. He wrote to me the following: "We hope you will be willing to share your perspective for an hour on what I would do if a national emergency required that spending for critical care was cut in half, and doing so without sacrificing either the clinical outcomes or the patient-family experience. Cutting the available dollars in half. which I can tell you is going to mean cutting people. So here are my 5 take-homes for you. First, we have a lot of technology in the ICU. We have rivers of data. It is very expensive. We have opportunities to create and deliver value. Understanding where the patient is in the state space, yeah, that does make a difference. Standalone boxes are not going to be helpful. Predictive analytics are important, but even more important are predictive analytics that detect anomalies so we can get on top of that patient right now and get them back to where they're moving. Finally, if you come to the healthcare environment with a solution, it has to generate value. The era of inventing a new toy, trying it out, and throwing it away if it doesn't work right is over. Show me how your solution helps me take more cost-effective care of my patients. Thank you very much. I think time is up, and I think we have run out of time for questions. It's been a privilege and my pleasure speaking with you this morning. Thank you.